Thank you so much for listening in and joining me here for giving me the opportunity to talk about parahydrogen-based hyperpolarization and the new developments we're pursuing at North Carolina State, where we pursue applications that range from biomedical imaging into novel physics to me, which have to do with RASER and laser effects. So I definitely need to thank all my collaborators that have been with me over the years and that have just been so important in all the conversations back and forth about trying to unravel and understand the experiments that we do every day. Now at NC State for 2 years with a wonderful group of people. And of course, without them, none of this work that I'm presenting here could happen. So a big thanks to them. This is the building where we currently work in. Of course, last week we just had a corona case in the building. So nobody knows exactly what's going to happen there, but hopefully things can continue with some amount of reasonability. So let me talk to you about parahydrogen in general as an introduction, how we can use parahydrogen as a source of spin order. And I want to tell you in the second part how we can use optical detection schemes such as rubidium vapor magnetometers or NV diamond centers to detect hyperpolarization. And then I want to tell you about a new development in the lab where we're designing hyperpolarization reactors that can provide hyperpolarization continuously. And they can also create this very long-lasting hyperpolarization by exploiting long-lived singlet states. And then in the last part of the talk, I want to introduce and talk more about the parahydrogen pumped RASER and how it allows us to apply, I guess, some mathematics from very different fields that have not been applied too much to the world of NMR before. We can now use these mathematics from other areas of science to these interesting interactions between hyperpolarized spins and electronic circuits. So I guess the other important part is that if you do want to interrupt me, please do, and just ask questions. I'll stop at the end of all of these parts to allow you to ask questions. So I think it is very important for us that work with spin physics, but then also with parahydrogen in particular, to really realize that all of these quantum discoveries are not all that long ago. So for example, Werner Heisenberg received his Nobel Prize for the creation of quantum mechanics only less than 100 years ago. And I think it goes to show that we still have a lot of new things to discover, and that there's many things obviously out there that we have no idea about yet, because this is really a relatively young field in general. And of course, also in NMR, even though it sometimes gets put as like an old science or a science that has been mostly developed and is now in applications. I think none of that is really true because there's still so many surprising effects we encounter day to day. And so it's just an encouragement for us to keep looking, to keep understanding, keep trying to find the ways of science to analyze all these fun experiments we do in all our labs. So Heisenberg in 1927, for the first time, wrote down the singlet state and the T0 state, which are so important in the description of parahydrogen. So parahydrogen is the singlet state of the spins. There's two nuclei, nucleus 1 and nucleus 2. And you can see here, this is the first time the singlet state got formulated in his paper from 1927. And as you can tell here, usually we would talk about the state as the alpha beta minus beta alpha state, but you can see here that even the way he wrote the state is a little different. He used these subscripts 1 and 2 to say alpha 1, beta 2 minus alpha 2, beta 1, which is of course just a different way, but it just goes to show that also our descriptions slightly change as we go through time. And then later on in 1935, after parahydrogen had been proposed and experimentally verified, there was a very, very nice book published by Adalbert Farkas, where he describes exactly the thermodynamics of parahydrogen and how it behaves as a function of temperature. And this is very important to us today, for all of us that use parahydrogen, because it explains to us how much hyperpolarization we can theoretically generate. And the partition function was written out in this book very carefully and detailed, which I plot here in this yellow curve. And you can see at 25 at room temperature, which is the higher temperatures here, which we normally operate at, we have 25% parahydrogen. And this makes sense because there's 4 total states. There's 1 parahydrogen state and 3 orthohydrogen states. So that's fully thermalized, represents the 25% parahydrogen. As we now cool down the system, let's say we go to liquid nitrogen temperatures, we get to a new thermal equilibrium in which we have roughly 50% parahydrogen. And so we can use this very efficiently to generate very large amounts of polarization in our spins. If we wanted to go all the way to a pure quantum state, if you wish, you can cool the system down, let's say, to 20 Kelvin, and then you're generating very close to 100% parahydrogen. It's kind of very fortunate for us that this curve here is pretty much flat at 100%, even up to temperatures of on the order of 20 Kelvin. So it's a really nice way of, you know, taking advantage of parahydrogen as a pure source of quantum order. And producing parahydrogen, just to do very simple experiments, is easy. All we need to do is take liquid nitrogen, submerge, for example, a coil like this one here that you see in the picture in liquid nitrogen. We fill this coil with iron oxide, and the iron oxide converts orthohydrogen to parahydrogen and vice versa. So what I mean is you can induce thermalization by filling the hydrogen in here, exposing it to the surface of the iron oxide, and then cooling it down, and thereby generating your hyperpolarization. The first time the parahydrogen induced hyperpolarization effects were kind of described in the literature, to my knowledge, is in this paper from 1983, where it was actually misinterpreted as chemically induced dynamic nuclear polarization, even though what is more likely is that they actually saw parahydrogen-induced hyperpolarization effects. So they were working with these interesting complexes and adding hydrogen to these complexes. And what was kind of interesting in these experiments that they couldn't explain at the time is that these experiments only worked on Mondays. So only on Mondays, they were getting these very strongly enhanced signals that you see here in C after doing a hydrogenation reaction. And only afterwards, now it makes sense that what must have been happening is that on the weekend, when the hydrogen was delivered, it was delivered from a filling station where they were filling the hydrogen at very low temperatures. And they must have also had some rust in their lines, inducing the conversion from orthohydrogen to parahydrogen, so that then they were actually using parahydrogen and observing these signals. So these types of experiments that were initially puzzling and confusing were then kind of understood later, as described by Bowers and Weidekamp in this case, 1986, where now everything was purposeful in the sense that a hydrogenation was conducted with parahydrogen on purpose to make propionitrile in this case. And then again, here you can see these typically antiphase signals that get generated from a hydrogenation reaction. And what is also nice is that also, the transfer from the polarization of the hydrogen to the substrates is also pretty simple, because all you need to do is sort of bubble some hydrogen gas through some solution and then expose it maybe to an ideal magnetic field, in this case, a microtesla magnetic field. And just wait for a little while for hyperpolarization to build up. So in this case, we typically waited for like 30 seconds or something like this. After those 30 seconds, the sample can be transferred into even a benchtop NMR spectrometer to get very high signal to noise. Because now to generate polarization, you don't need a strong magnet anymore. Any magnet will do now to do good detection of this high polarization level that gets generated. So I wanted to show something that we recently did, which is like an automation of the system. The parahydrogen is the sample is shuttled into the magnetic shielding that is on top of the magnet, where the polarization is generated. It gets shuttled back down, and then we can do the detection. Just to show that this polarization method can also be easily automated, and we can reproducibly generate this hyperpolarization. So now the only question is, how do we introduce this hyperpolarization into other chemicals other than hydrogen? And so basically what happens when we bubble through the solution? And there's two sort of famous ways of doing this. One is via hydrogenation, and the other one is, of course, the Saber technique, signal amplification by reversible exchange. So let me just say some simple words about how to introduce parahydrogen through hydrogenation here. So imagine you take the parahydrogen here in purple pink, and you introduce this parahydrogen onto a double bond, say with a rhodium catalyst. You conduct a hydrogenation reaction. Now you've introduced these two highly polarized spins on this molecule. And if you now say, for example, do this in a very low magnetic field, then you allow the polarization to flow through the J-coupling network across this molecule, and all of the spins in the molecule can be hyperpolarized. The other method that I'm extremely fond of, that I started working with roughly in 2010, when I was still in the Pines lab, shortly after it was published from Simon Duckett at York, is signal amplification by reversible exchange. So here, what happens is that parahydrogen is in reversible exchange with an iridium complex, meaning the hydrogen kind of pops on and off, And so does the substrate. The substrate is on the right, in this case, pyridine, and it also kind of pops on and off, What matters is the average lifetime of the complex in the middle. You can imagine that you want kind of something that is short-lived in order to make this thing very efficient, right? So the faster you go, the more exchange events you have, the more molecules participate, and therefore you would think, well, that would help hyperpolarization. At the same time, you need to also have enough time to allow for polarization transfer from parahydrogen, that is here in red, then, for example, onto a nitrogen-15 or onto other spins in this molecule. So it's a very careful balance between enough time for polarization transfer and exchanging fast enough in order to have a very efficient polarization buildup on the substrate. One of the things that we recently did in order to kind of understand exactly what controls the kinetics of these Saber reactions is to go forward and do very careful ab initio calculations that describe how we go through these various species that may exist in the Saber, I guess, on the Saber energy surface. So you see here in the bottom, A1, this is the complex that you just saw essentially on the previous slide, where we have the two parahydrogens that transfer polarization to pyridine. But then, of course, we need to kind of replenish the parahydrogen every once in a while. This reversible exchange has to take place. The same is true for the pyridine. The pyridine has to come off in order to be able to get a new substrate molecule in here. So we calculated very carefully the various possibilities that this hyperpolarization transfer species A1 has in terms of its energy landscape. So one thing that happens often is, for example, that a solvent molecule, methanol in this case, would actually replace a pyridine on this iridium. Next, the pyridine also really likes to just dissociate, forming a species that can now immediately absorb a second hydrogen moiety, which then can swap. So if you compare A2 and A2 prime carefully, what you see is that the molecule that just came in, the H2, now becomes a real hydride, whereas the hydrides that are in the back attached to the iridium, they now have formed an H2 molecule, and which can now leave. And this is the pathway that makes new, fresh, hyperpolarized parahydrogen come into these systems. And so we're very excited to kind of unravel exactly what the energetics of this is. And we find exactly also what the energy barriers are in these systems, which really allows us also sort of from first principle to calculate exchange rates in these systems, and will allow us moving forward to design new systems that can also display the Saber process, because we now understand the fundamentals of the system much better. And one important way that we think can contribute to helping this process is also just by visualization. So I have two links here that where we display exactly the minimum energy pathway of, for example, the pyridine exchanging. As you can see here in this reaction, the pyridine is leaving. So I encourage you to click on these links. And I can share with them with you later when we go through this. The other thing that is very important is not only the energetics, but also the spin physics. Sort of not only the chemical evolution, but also the, I guess, nuclear spin evolution. To understand the nuclear spin evolution, we spent a lot of time trying to, in very much detail, understand the Hamiltonians that govern these systems. So think of A and A prime here as the two spins where the polarization comes from. So A and A prime are the hydrogens. This is basically where the singlet state is in the beginning, the parahydrogen state. And then the question becomes, how do we transfer polarization to another set of spins, namely the B spins, B and B prime. And the important interactions that are present here are the J couplings, but also the frequency difference between the A spins and the B spins. So the driver of polarization transfer is actually the symmetry breaking that happens in this kind of an arrangement. So of course you have interactions between all kinds of spins, but what is the interaction that breaks the symmetry is the question. And what you can see is that spin A couples with a J coupling that I call here J prime AB to the spin B prime, whereas it couples with a J coupling JAB that is different to the B spin. And this is what breaks the symmetry fundamentally. And this is what this element here is, delta JAB, the difference in J coupling between, I guess, the horizontal versus the diagonal J coupling in this picture. And in order to really understand this and to be able to look at these Hamiltonians, also another important point is to choose the right basis in which we can really visualize the dynamics. So most of you are aware of the idea of singlet states, such as up, down, minus down, up, for example, and then the triplet states. If we now have a four-spin system like this, what we do is we can sort of generate other sets of spin states. For example, a state where the A spins are in the singlet and the B spins are in the singlet too. We would call this state the S0 state. You could, of course, also construct a different state with a different name. Let's say the A spins are in the state T plus and the B spins are in the state T minus. So this is how the nomenclature of these various states now comes into being. And if you have 4 spins, you have a total of 16 states. So there's 16 different possible combinations that I'm not showing here. But once you've chosen a good subset, then you can actually start sort of connecting to concepts that we're more familiar with, such as rotations on the Bloch sphere. So for example, here, I use the combination of the singlet-singlet state and its connection to the T plus T minus state, for example. The singlet state, here marked in red, this is the source of polarization. This is your parahydrogen state. And so the question becomes, in this Hamiltonian, if we depict it this way and we chose this basis, we can make this representation. Then we can represent the transfer of polarization as a simple rotation on a Bloch sphere that we're kind of a little bit more familiar with, where now the Hamiltonian is pointing, for example, here along the minus y-axis, and then the density matrix simply rotates around this Hamiltonian if we choose the right magnetic field. And this is an insight that was very important for us in order to be able to hyperpolarize all kinds of spins, not only protons, but also nitrogen-15 or carbon-13 efficiently. So if you write down this Hamiltonian carefully and you develop an appreciation for this picture, then you can actually conclude that the right amount of magnetic field that you need for polarizing, for example, nitrogen-15 is on the order of 0.5 microtesla. So how exactly does that work? Let's have a closer look at this Hamiltonian. For most efficient hyperpolarization transfer, or in order for this image here to be true, you want the Hamiltonian to only have the X component, but no Z component, essentially. So what this means is that you want on this Hamiltonian only things that are on the off-diagonal elements, because those are the things that drive the polarization transfer. And not surprisingly, as I said on the previous slide, the element that occurs here is this delta JAB, the symmetry breaking element. So what we need for polarization transfer is basically the difference between the on-diagonal elements to be 0. This is what would establish resonance. So the resonance condition, the way we derive it, is simply by stating that the diagonal elements have to be equal to each other. And this is this equation that I showed down here. And so if we just make these to be equal, and then we solve for the magnetic field at which this is true, then we arrive at this very low magnetic field of 0.5 microtesla, which is why you saw in the video that we use magnetic shielding to establish these very low magnetic fields that are lower than the Earth's magnetic field. And so the big gain or win from this insight is that now we can hyperpolarize many, many molecules that just have these exchange reactions with the Saber catalyst. And one thing that we did most recently was to look at a subsets of antifungals and cancer drugs, for example, here. Here we chose voriconazole, clotrimazole, letrozole, and fluconazole. Clotrimazole, many of you may recognize simply from a cream that you might be putting on your feet every once in a while. And what is interesting in these systems is that it didn't take very much for us to get this right. So essentially, the first time we tried to hyperpolarize these molecules, they immediately showed hyperpolarization in these systems. And I think this is, in my mind, one of the most important sort of insights here, that with this kind of Saber approaches at microtesla fields, the range of molecules that you can hyperpolarize is just very large. The one thing that is important is to get the magnetic field right. So here I show hyperpolarization is a function of magnetic field. So how exactly we adjust the magnetic field inside of these magnetic shields. And this is a little different for the various compounds. In particular, compare the three elements that have these sort of 5-membered rings: voriconazole, clotrimazole, and fluconazole. They all have the nitrogens in these 5-membered rings. Versus letrozole, that has a cyano group here, which shows slightly different field dependence. So you can actually see that it is, in some cases, necessary to optimize the magnetic field just a little bit in order to get the optimum hyperpolarization. Okay, I guess I'm going to take a small break here for any questions that may exist.
All right, so we'll be taking in questions now. We have one question from Reza Dervisoglu, which asks, what is the operation window of Saber in terms of time?
The operation window. I'm not exactly 100% sure what it means, but there's maybe two different questions here that I can answer. So to build up the hyperpolarization, so how quickly can you make the hyperpolarization? It depends a little bit on the substrate, but it's typically on the order of 1 minute. So 1 minute of bubbling typically establishes maximum hyperpolarization. The other question that I could imagine what the time window refers to is, once you make this solution and you start bubbling and you generate hyperpolarization, and then let's say you detect it, then you've used it once, but then you can actually just bubble through the solution again at a later point in time and regenerate the hyperpolarization. And that's the process you can do for days. So sometimes even after a weekend of leaving the solution alone, I would come back into the lab and bubble through the solution again and generate hyperpolarization again after a day or 2 or 3, like after the weekend. Now there's one other way of understanding the question, which is, how long does the hyperpolarization last once it leaves sort of the hyperpolarization region, once you don't bubble parahydrogen through it anymore? And in this context, we have developed long-lived states that can sort of contain the hyperpolarization for a long time, so that you're dealing maybe with decay time constants between 1 minute up to 20 minutes, so that you have, maybe 5 minutes or up to an hour where you can actually still use the hyperpolarization, even though you're not actively pumping it anymore. I hope that kind of answers one of his possible questions.
Yeah, we have a few other questions, like Jeffrey Bodenhausen asks, what do you mean by a negative field?
Oh yeah, what I mean by negative field, yeah, it's kind of a confusing concept because obviously there's not really a negative field. In this context here, it's really, we're doing a polarization transfer experiment. So we have a magnetic field inside of the shields that could be in the same or in the opposite direction as the magnetic field inside of the NMR system where we do the detection. So positive and negative magnetic field only indicates a relative direction between the magnetic field inside of the shields versus the magnetic field in the detection region of the big NMR magnet where we do the detection.
You have another question from Christopher Clegg. Were these compounds 15N enriched?
No, these are just natural abundance. So we just purchased the compounds straight off of the catalog and put them into the solutions. So they're all with nitrogen 15 at natural abundance, which is on the order of 0.3%. I want to actually make one comment about that question. So let's consider these various molecules, as you can see here. You see that the polarization that we observe is typically only on the nitrogen that binds directly to the Saber compound, right? So for example, if you look at this fluconazole group right here, this nitrogen binds, and this is where we observe the hyperpolarization. Whereas the two nitrogens that are in here in the back, they don't bind to the iridium, they are not observed. If this were labeled, if this were all nitrogen-15 labeled, then we would actually see hyperpolarization from all of these. One problem is that if you have this at natural abundance, and this first one, the one that actually binds to the iridium, is nitrogen-14, it's a quadrupole, then this quadrupole actually eats all of the hyperpolarization and relaxes it away, which makes it such that it cannot arrive at the nitrogen-15s in the back. So there actually is a very big difference between having natural abundance where only one nitrogen-15 is labeled or a fully labeled system. A fully labeled system will allow you to sort of have the polarization spread much more throughout these molecules.
All right, so I think we have one last experimental question and a few theoretical questions after that. So Julia asks, what is the reproducibility of Saber? How can I be sure that I get the same enhancements after repeating the procedure?
I would say plus minus a factor of 2. so reproducibility is not within a few percent or anything like that. Small little changes in sample preparation, some little, there's definitely issues there. Controlling all the parameters on these systems, exactly the amount of parahydrogen you're making, exactly what kind of contaminants may exist in various places, that's a little challenging. I would say what is reproducible is whether it works or not, kind of a thing, right? Like whether you can see the polarization or not. That's quite reproducible. And very experienced researchers, after many years of doing this very carefully, they will be able to do this very reproducibly. But in the beginning, if you're a beginner and you start doing these experiments, you can't really expect a ton of reproducibility in the beginning.
Thank you. We have a couple of theoretical questions now. Gabriele Stevanato wants to know, is there an explanation for the different field dependence of different substrates?
Yes, there is. It has to do with the binding strength. So the letrozole, and it also actually has to do with the adiabaticity or non-adiabaticity of the transfer from polarization field to the magnet. So let's think about the width of these shapes first of all. So for example, voriconazole, clotrimazole, and fluconazole, they have wider shapes compared to the letrozole. And this is because the letrozole binds tighter to the iridium, and therefore the resonance condition is better defined. So you have a larger time for doing the polarization transfer on the complex, which leads to a more tightly defined polarization transfer field. Now, the other thing that is different in these shapes is that letrozole is relatively symmetric around 0, whereas fluconazole, clotrimazole, and voriconazole are not as symmetric around 0. And this is actually because of this problem of whether the magnetic field in the shield and in the detection magnet are aligned or not, because it makes a difference in the suddenness or adiabaticity of the transfer from the hyperpolarization area into the magnet upon transfer. So the details of which I don't want to go into right now, just because it gets complicated.
Okay, we have a few other questions. So Walt Masevsky wants to know if there's a way to sweep the microtesla field similar to a CP ramp to always hit the polarization transfer maximum.
Yes, that is a very good suggestion, and we have done that. And I think especially actually from the group of Malcolm Levitt with some hydrogenation reactions, there's a very nice paper that adiabatically ramps through the resonance transfer conditions and generates very high polarization levels this way. So it's certainly possible. With Saber in particular, I have not seen a very large improvement by doing ramps. What we have seen though is that we could implement a sort of pumped scheme where we just turn on the proper polarization transfer field for a short amount of time, then turn it off and turn it on again. And what it does is it kind of allows separation of the right timescales for the chemical reaction and the right timescales of the polarization transfer. So you're pumping the polarization transfer as most efficiently as it goes, and you're giving the chemistry enough time to refresh. And so with these kind of pumped approaches, you can actually up to double your polarization levels instead of just having a constant microtesla magnetic field.
Thank you again. So for now, we have 2 simple questions and 2 questions on exchange. So Madhu Bassetti wants to know, is there any data on 13C compounds polarization with parahydrogen?
Sorry, can you please repeat the question?
Yeah, is there any data on 13C compounds polarization with parahydrogen?
Yeah, so carbon-13, also with the microtesla approach, works well now, for example, for pyruvate or lactate. So we can hyperpolarize the carbon-13 also through the Saber sheath approach. One difficulty here has been in the past that oftentimes these types of compounds, say lactate and pyruvate, don't exhibit the good exchange rates that you would have with a nitrogen compound, so the chemistry is a little bit different. But as Simon Duckett has demonstrated, is that by addition of DMSO into the solutions, you impact the chemical exchange in such a way that you speed it up a little bit because previously it was too slow. And you can actually make Saber efficiently also work for carbon-13 compounds.
Shiraz Nantagma wants to know, does the Saber technique work with ortho-enriched hydrogen?
I believe the answer is yes. It's not something I have tried, but I do believe that there are a few papers that describe that effect. This is just sort of a vague recollection at the moment, though. But I don't see any reason why it shouldn't work. Yeah.
And the final 2 questions, I don't think we can take any more for now. Thomas Robertson wants to know, for the energy diagrams, have you observed exchange of the pyridine trans to the carbene experimentally? And he adds, I think this was A3 prime.
So the question is whether I have observed experimentally the exchange of the pyridine in the bottom. Is that the question?
Yeah.
Okay, so experimentally,
exchange of the pyridine trans to the carbene. Yeah.
Yeah. So this bottom pyridine, which is the one that is trans to the carbene that is on the IMS, this exchange does happen, but very, very, very much more slowly than the pyridines that are sort of in the horizontal plane. In the calculations, that was a pathway that was basically excluded. It's clearly energetically very much disfavored to exchange this in bottom, but that does not mean that it doesn't occur at all. It certainly occurs way too slowly to be efficient in generating Saber hyperpolarization.
Thank you, Thomas. And the last question before we move on to the second part of your talk. We have a question asking, in which way can you describe H2, which has been dissociated from the organometallic complex after the singlet state is broken, in terms of its quantum states and Saber conditions?
Yeah, so one thing that is typical, and there's various pathways of what happens in the polarization transfer, but let me, in order to answer that question, return maybe to this diagram here. So this illustrates one possibility here. So let's say you start in this particular state where you have parahydrogen in the singlet state, and now you transfer this into a state that you would characterize as the T plus T minus state, meaning T plus on the hydrogen and T minus on the nitrogen. What this means is that the nitrogen is now negatively hyperpolarized, but it also means that the hydrogen that is about to dissociate is also hyperpolarized in its T plus state. And this is actually also something that is often observed in the experiments, that not only do you create an imbalance of polarization on the target spins, that ones that you want to hyperpolarize, but you also create an imbalance of polarization in the hydrogen itself. So, for example, the T plus state gets hyperpolarized in the orthohydrogen, so that within the orthohydrogen, you also have excess hyperpolarization that you can now observe in the experiment, and you see hyperpolarized orthohydrogen in that sense.
Right, that was a wonderful answer and a wonderful series of answers. So I think we can move on to the second part of the talk now.
Okay, good. All right, so in my second part of this talk, I want to talk a little bit about a development that I'm personally extremely excited about, which is to move towards sort of handheld NMR, may it be for metabolic screening, chemical analysis, or alike. Similarly, one thing that you can imagine moving forward is to build an NMR microscope. So imagine you have a microscope that not only tells you about everything about the structure that you can see in normal microscopy, but you can actually get an NMR spectrum from every point in your image, in your microscopy image. And I do think that by combining sort of optical techniques with Saber hyperpolarization or Parahydrogen hyperpolarization, or probably any hyperpolarization approach for that matter, you might be able to actually do this. So I want to talk to you about rubidium vapor magnetometers that can be used to detect NMR signals at very low magnetic field, as well as an NV diamond approach where we can have a beam that we can possibly scan across the diamond and therefore acquire an NMR spectrum from various spots of a sample that could maybe set a new stage in the world of microscopy. So let me start with that topic where nitrogen vacancies that fluoresce are used to measure magnetic fields. So here we have a diamond lattice, one nitrogen defect, so a nitrogen instead of a carbon. And what that leads to is that you have a vacancy with very special spin properties. These vacancies are typically spin 1 particles that respond to magnetic fields. And this is what you basically see here in the bottom of this diagram. You have the MS equals 0 state, and then the +1 state that can be split by a magnetic field. So you can see that the distance between the MS +1 state and MS -1 state depends on the magnetic field. And so now if you probe the system optically, the diamond, then the fluorescence that you can observe in the system will depend exactly on the distance between these two spins. So how does that work? So let's think about that for a moment. So you see this green arrow and you tune, this is a microwave that you apply between the MS equals 0 state and maybe one of the split states. So let's say we choose the MS -1 state. So now with this microwave present, you'll get a certain amount of fluorescence out of the system. If now the magnetic field changes just a tiny bit, that means that the position of this MS -1 state here in the bottom changes. And therefore the intensity of the fluorescence in the system overall will depend on exactly the magnetic field, and you can see that. So why is the magnetic field changing? Why am I talking about that? The reason is that the hyperpolarized substrates, they emanate a magnetic field that we want to detect. So now if the magnetic field is coming from these little samples, wiggling on this MS -1 state, then we can see that and detect an NMR signal essentially. So Nitya in the lab of Ron Walsworth has kind of put together the system with our assistants. We sent our favorite Parahydrogen polarization making system to her. And then she put together this capillary system here, where inside of a cuvette, a little window was inserted that contains this diamond. And then this cuvette was filled with a Saber solution to generate the hyperpolarization simply by bubbling the parahydrogen through the solution. And you can see sort of the various components that are needed here. Sort of the RF coils to apply pulses to the spins. Then also what was needed was a microwave close to the diamond. And then obviously the polarization simply by bubbling parahydrogen through the system. And since these were the very first experiments that were done in such a way, we were looking at signals, but we needed to convince ourselves that this is actually real NMR signal. So the very first thing that you typically do in order to identify whether this is a real signal or just some kind of fake artifact is that you check whether the signal actually changes as a function of magnetic field, as you would expect from an NMR signal. So here we're changing the magnetic field slightly, and the frequency of the observed peak, which is in blue, changes accordingly, which is depicted in this pink line. So that gave us confidence that this is very likely a real NMR signal. And once we quantified the enhancement, we saw in the order of 144,000 times enhancement with 50% parahydrogen. Now, this large number, I will point out, is possible kind of only because we work at a low magnetic field of 6.5 millitesla, right? So generating a large enhancement is much easier in this case than it would be if we were working at a very high magnetic field, obviously. So now we also examined what happens if we decrease the concentration of the Saber substrate in these solutions. So we worked at 100 millimolar, which gave us very nice signal, and then went down with the concentration of the Saber substrate. And you can see that the signal decreased accordingly. And we're actually currently working on kinetic models, sort of based on this energy landscape I described in the previous part, that can exactly explain the concentration, the behavior of the polarization as a function of concentration, which is not exactly linear, just approximately so. But what we're very happy with is that we established sort of a record proton number sensitivity of 66 femtomole per root hertz detected with these NV diamond centers. And this was just recently accepted at PRX Quantum. Another thing that we wanted to demonstrate is that even though we work at very low magnetic fields of only 6.5 millitesla in this case, we can still do chemical identification. For example, by taking advantage of the work. So for example, here we took nitrogen-15 labeled pyridine, which has a J coupling between the nitrogen and the proton on the order of 10 hertz. And we could see the splitting in the NMR signal. We also wanted to demonstrate that not only pyridine can be detected, but also biomolecules such as nicotinamide. And indeed, we see this peak here. So in the next subpart of the talk, I'm not going to switch to using rubidium vapor magnetometers to detect Saber signals. And in this work, it's a little bit different in that the detector, the NV diamond, was previously in immediate contact with the solution, which is really attractive because it means that you can really do sort of this micron scale work where the detecting spins are extremely close to the Saber spins that you're trying to detect. Whereas with the rubidium magnetometers, they are much more sensitive in absolute sensitivities, but you cannot bring them as close to the sample. They have to be heated, and so you can't exactly mix rubidium vapor with any kind of random solution. Therefore, there has to be some separation, which is sort of the downfall of this, even though the absolute sensitivity is actually orders of magnitude better than the NV diamonds. But with this kind of a system, we can certainly envision, because of its increased sensitivity, sort of general chemical analysis that is portable. So here, a rubidium vapor is used, that it gets pumped optically, again, with lasers, and it becomes extremely sensitive to small magnetic fields that emanate from the Saber solution. And with this type of a system, let's say, again, we use a similar compound, or the same compound rather, nitrogen-15 labeled pyridine, with this J coupling on the order of 10 to 11 hertz. Then you can get a very highly resolved NMR spectrum from these rubidium magnetometers, where the NMR frequencies are absolute frequencies here depicted, where in this particular case, we're dealing with a, I guess, AX2 system, so, or XA2 system, so meaning one heteronucleus strongly coupled, or most strongly coupled, to two other spins. Always when you have such a combination, you see the strongest line in your NMR spectrum at 3/2 the J coupling, and that's exactly what you see here. You see the peak appears roughly at 16 hertz. This is the most predominant peak, and this is because of the fact that you're dealing basically with this combination of one spin plus two other spins that it couples to. One thing that we're also doing now, which is also something that makes an easier point of entry into these devices, is to use commercial devices such as the Q-spin, and very carefully think about what happens at very weak magnetic fields when we apply some perturbing magnetic fields at these low magnetic fields. So meaning, if we're not exactly at zero, where only the J coupling is active, but we just add a very small, tiny amount of magnetic field, what happens in the NMR spectrum? So one of the simplest cases is formic acid, where we have one carbon-13 and one proton, for example, which gives us a peak at 1x the J coupling. So in this case, at 225 hertz roundabout. This is if there's no magnetic field. And now we apply a weak magnetic field, which splits these lines into two. And we can observe the splitting as a function of magnetic field, which is plotted in this insert. So you can see we very slowly, in a few milligauss, increase the magnetic field, and you can see the splitting of these lines getting larger and larger. So one thing that is important in this slide is that here the magnetic field was applied 90 degrees away from the direction of detection. And we're kind of exploring this effect now by simulation. So basically what happens if we apply the magnetic field, the perturbing magnetic field, 90 degrees away from the detection is that then you observe the splitting, because the lines that you observe are between the singlet state that is in the bottom and the T plus and the T minus state. So if you change this picture and you apply the magnetic field along the direction of detection, then on some level, you're actually controlling the selection rules, because now the more appropriate description for this problem is that you're detecting peaks between the singlet state and the T0 state. And this, of course, doesn't split if the states on the outside change. And so we're kind of playing with these selection rules and how we can manipulate these zero field NMR spectra. So again, we take a different case, for example, acetonitrile, where we have a zero magnetic field NMR spectrum. This now has actually two peaks, one at 1x the J coupling, which is here, and then one at 2x the J coupling, which is here close to 275 hertz. If you again apply a magnetic field 90 degrees with respect to the direction of detection, then you observe a lot of splitting, a lot of additional lines that form. And we confirm that again by simulation. That's shown here on the left. This is exactly the behavior here on the bottom that you saw also on the previous slide, where the bottom line splits into a doublet, whereas the lines at 2x the J coupling splits into a more complicated pattern. if you now apply the magnetic field, the perturbing magnetic field along the direction of detection, then you see the line in the middle doesn't split, but the line at 2 times the J coupling splits in a different but also interesting way. And so simply by playing with this relatively seemingly sort of simple angle, you can get these various NMR spectra. And we're kind of exploring the details right now of how these selection rules can be best controlled and how we can extract most information out of these zero field NMR spectra in this way, simply by changing the direction of detection. So this is, I guess, another good spot for a break, and maybe some more questions if you guys wish.
Yeah, we're ready to take questions if anyone has them. Yeah, that was a very interesting part of your talk with the detection along the magnetic field axis.
I also see that kind of way over time already. So probably, right? So I'm not really sure how much longer we want to continue. I guess it depends sort of
surprisingly,
on the level of interest.
We don't have any questions yet, so I think we can move on with the talk.
So I want to now, I guess, transition a little bit to the idea of biomedical applications and the current limitations that current hyperpolarized imaging approaches have. Well, they may or may not be limitations, but certainly something to think about is that currently the signal lifetime of the pyruvate is that it gets injected and used is relatively short, with a lifetime of 45 seconds. And also that we're doing bolus injection, which does not really allow us to observe steady state metabolism. And to address these issues, we're kind of trying to create a system that has continuous hyperpolarization that we can continuously inject, and also that generates very long-lived hyperpolarization. And so for this purpose, we've developed a new, I guess, engineered a new device that we call the spin transfer automated reactor, which we also call the STAR system, which gives us this kind of continuous stream of hyperpolarization. And I want to kind of just briefly explain what's at the heart of the system. So we have a tube-in-tube system where the outside is just normal PTFE tubing. And then the inner tube is made out of a very thin layer of porous Teflon, which has the wonderful property of very, very fast hydrogen diffusion through it. And basically methanol stays stuck on the inside. So we flow in the inside of this tube, we flow the Saber solution. On the outside, we flow the parahydrogen. The parahydrogen can easily diffuse in and out of the solution and happily exchange. And so we just pump the solution through this system that is just coiled around this system here in the bottom, and we control the magnetic field, say with shielding and some coils that we install. And then we can continually just pump the solution in a circle forever and observe NMR signal in our NMR for as long as we want, essentially. And so I just wanted to very briefly show that this works but relatively well. For example, we use pyrazine, which is nice because it gives just one singular line because all of the protons are chemically equivalent. And we observe relatively large polarization levels and enhancements. Also, this works for nitrogen-15, for example. Here is metronidazole, which is an antibiotic drug, and all of the nitrogens hyperpolarize. One thing about metronidazole that I always find particularly interesting and curious is that the nitrogen-15 that obtains most hyperpolarization is actually this one in the nitro group that is actually very far away from the place where the Saber catalyst binds. So the Saber catalyst binds to this nitrogen. But now we have a fully labeled nitrogen-15 system, where the polarization can easily flow everywhere without getting quenched by any nitrogen-14. And in this nitro group, we have a particularly long lifetime of 10 minutes or more. And therefore, we can build up a large amount of polarization in this nitro group in this molecule directly at the room temperature solution. And this is why this is the largest peak here in the spectrum. Also, carbon-13 works, as I discussed earlier, following the work of Simon Duckett, by adding the DMSO into the system. So this is what you see, the X. We add a little bit of DMSO into the solution or other sulfoxides that now bind on the bottom of the iridium complex, modulating the exchange rates to make it just right for pyruvate, and giving us, for example, long-lived singlet states on the pyruvate directly simply by bubbling parahydrogen through the solution. And this is also why you see these antiphase patterns indicating that your signal comes from a singlet state. Also for this compound, we can do magnetic field studies where we see what happens at various applied magnetic fields in the microtesla regime. And we're currently in the works of generating the exact theoretical analysis of predicting this magnetic field behavior here that you observe on these two carbon-13 sites. And another point to make is that because with parahydrogen, you start from the long-lived singlet state, you can induce these long-lived singlet states directly in other spin pairs, such as the pyruvate, as you've seen on the previous slide, but also on these diazerine complexes, which are still, to this day, the ones where we have achieved the longest hyperpolarization lifetimes on the order of 23 minutes. But as I said, you pyruvate, but you can also do this, for example, on systems like these, where the polarization doesn't flow directly from the parahydrogen onto the long-lived singlet state, but it actually has to kind of go through a network of spins. For example, in this case, it has to flow through this pyridine ring where there's additional protons. And what is fascinating is that if you work at low enough magnetic fields, that then indeed you're able to sort of propagate singlet states. So instead of propagating polarization through these systems, you're actually propagating these singlet states that can then end up in, for example, very specialized carbon-13 spins that can bear the hyperpolarization for a very long time. Another piece of work that I'm particularly happy with is where we generate, but then also detect the hyperpolarization at the very low magnetic fields. For example, at 1 millitesla, 4 millitesla, 10 millitesla, and 1.1 millitesla. So this is done in an electromagnet where we can arbitrarily choose the magnetic field. And you can see that even though we are at very low magnetic fields of just a few millitesla, because we have these interesting spin structures with, say, carbon-13 and protons or nitrogen protons, that this gives you so much splitting. And because it's much easier to shim sort of low magnetic fields, we can get highly resolved spectra that can help us do chemical identification at low magnetic fields. And I think this is a very important step in order to be able to, make NMR more general and portable in the sense of getting good information, even from cheap magnets. Now, this is the transition to my next topic. So maybe I'm going to just stop one more time and see if you guys are still okay listening to me, or if you want me to just answer some questions.
All right, we have a couple of questions. Andrei Pravdivstev, he wants to ask, your observation of signal as a function of pyridine concentration, was it explained or exemplified by Knecht et al. In RSC Advances 2016?
Yeah, so I'm sure that using those theories in there can help us explain the observed behavior. And as a matter of fact, since the question comes from Andrei, I would very much maybe appreciate a conversation in more detail about how we can go about this. This is certainly something of high interest at the moment to us, of how to optimally describe the kinetics and then especially the sort of the concentration dependencies of this. I don't have the direct answer right now, but I'm very interested in a conversation about that.
Yeah, and another question is from Roman Frutos. If we take, say, formic acid at 0 field, it has a single line at roughly 222 Hertz. Is it possible to increase the SNR of this peak by simply applying a field on the sensitive axis, which will not split the line?
Okay, so I guess what I will say about that is these rubidium vapor magnetometers, they're actually most sensitive at the low magnetic field when you're not applying an additional magnetic field. So if you do apply a magnetic field along the direction of detection, then just because your rubidium vapor magnetometer becomes less sensitive as you apply that magnetic field, you're kind of hurting yourself. So the highest signal to noise in this particular configuration you'll probably get actually at 0 magnetic field without applying a magnetic field.
Right, that's wonderful. That was the last question, and now we can move on to talking about RASERs.
Yes. Okay, so in this video, what you'll see is what happens if we continually pump highly polarized solution into an NMR system. So let me see if I can actually start the video. That'll be the biggest challenge of this entire thing. I kind of feel like I need my mouse somehow here.
This is the currently operating box just next to the spin solve. Currently, the solution is just pumping through the system. And then if I go on to expert software and I hit run and acquire for here, I'm acquiring for just 13 seconds to get a quick RASER. RASER effects. We're shifted a little bit off here just because I've been acquiring for a long time. I need to shift the frequency a little bit back and the shims are off, but the shimming does become an issue.
So yeah, so as you can tell here, this does not look like a normal FID, but we're seeing this RASER effect where we have a large amount of polarization. And then as soon as we open the acquisition, we see these interesting signals that start just oscillating and continue forever. And they currently are just limited basically by the acquisition time of the spectrometer. And I feel like this is giving us an interesting opportunity to maybe use NMR for precision measurements where you need to detect a certain frequency for a very long time, or just for exploring, for say, a J-coupling network with very exact values. And I think this is where Saber and FIB, for example, are particularly valuable because this gives us the access to a RASER, not only from, say, things like xenon that don't interact with other spins very much, but within a molecule where we can really explore sort of interesting chemistry. And this work, of course, originally sort of was put out by my collaborator and friend, Stephan Appelt, where they described the system. And in one of their publications, they compare the RASER versus the laser. And I think this is sort of pretty insightful comparison to make. So in a laser, you have an optical resonator, meaning a mirror, where its separation essentially controls the frequency of the light that emanates from the system. And inside a system, you can create a population inversion, which we use the letter D for, and it's also associated with some kind of relaxation rate. And of course, the other thing that is very important in the laser is, of course, the energy separation between the states. And in a laser, that's on the order of 10 to the 14 Hertz, a very large frequency compared to any kind of NMR frequency. On the RASER, on the other hand, this frequency, of course, as you know, is not 10 to the 14 hertz, but it's just a few kilohertz or a few megahertz. A few kilohertz if we work in the millitesla regime, and of course, several hundreds of megahertz if we work in a high magnetic field. So for the RASER, of course, the entire system is also set up differently. You don't have a mirror, right? So all we have really is just an electronic circuit. We just have a coil. And what is important in this coil is that it have a very high Q in order to be able to very strongly respond to the spins. And also the pumping is very different, of course, in a RASER. It doesn't come from some kind of light source that you pump into the laser, but instead our pumping is actually the parahydrogen that we bubble through our solution, which establishes the population inversion, D, which is what we need for the RASER effect. And one of the most critical equations here in this context is the question, how high does your polarization have to be in order to kind of get to these RASER effects? So at what point in time, when you generate very large polarization in your systems, do you actually observe these strong interactions between the spins and your electronic circuit? And this is basically the equation that governs that question. So if your goal is to actually get a RASER, it may not be, right? Sometimes these effects might be very annoying and you don't actually want to have them. So let's say you want to measure just the polarization level and that's what you care about, then you don't want a RASER. But if you want to establish a RASER, then what you would want is a very high Q, a very high number of spins, a very long T2, large gamma, a good filling factor, and then these are, of course, just the famous constants. And once you establish this polarization that goes above the set value of this equation, then you can see these kinds of interesting effects. And this slide here, in particular, illustrates sort of the important difference of using a Saber or a FIP system versus using like a xenon or helium maser, for example, which is that you can get many different lines and actually sort of do precision measurements. Okay, so what are we looking at here? In white, up top, you just see the NMR spectrum acquired at a millitesla magnetic field from nitrogen 15 labeled pyridine. If we now start bubbling parahydrogen more strongly through the system, you can see here what happens as a function of bubbling rate. So meaning higher and higher pumping, we're getting more and more population inversion. You see we bubble at 70 milliliters per minute, 90 milliliters per minute, or 400 milliliters per minute. And the more bubbling you get, the more of these lines become high, gain high enough polarization in order to generate these RASER effects and just continue forever, as you can see here in the time domain signals. So at a flow rate of 70 milliliters per minute, one of the lines goes over the threshold. Then you go higher in the pumping rate, a second line appears, and then you pump even higher, and then you have 4 lines that go over this threshold of raising, and you can see these lines go on for a very long time. Together with Adjunct and Stephan Appelt, more recently, we've worked in sort of a new realm. We're kind of entering this kind of new realm of using the mathematics of coupled differential equations to describe what happens. And things are not always as orderly as you wish, as you've seen on the previous slides, but sometimes things can be chaotic. You can see effects of intermittence and all kinds of really strange things that I certainly myself haven't seen before, and I'm really excited about exploring them in more detail. So for example, here in this funny FID, where things change as the polarization level decreases slowly, in the beginning, you have a rather chaotic behavior in the time where both A and B spins in the spin system are being observed. And then at a later point in time, where there's a second burst of this RASER, only frequencies associated with one particular spin are observed. Then this decays again, and there's a second burst at a later time where only the only the frequency associated with the other spin are being observed, and it goes back and forth, back and forth. So this is the typical sign of intermittence, which can be explained with the mathematics of chaos theory, and we're kind of working out in these couple differential equations. And we're kind of just entering this world, and I just want to kind of show you some of the typical parameters that govern the behavior of these systems. For example, the important parameters are the population inversion, which is essentially the amount of negative polarization that we generate. The pumping rate, so how fast we pump parahydrogen into the system. The T1 times are extremely important in these for the behavior of these systems. The coupling constant, which quantifies basically the coupling between the spins and the coil. And then, of course, also the electronics of the coil itself matter, which are dictated by the resonator damping rate, which is essentially just the inverse of the Q of the coil. And then, of course, also the T2 star time. So basically also like your shimming, because it's T2 star, like how well you've shimmed the system will also make a difference in the behavior of these systems. But when you kind of write down these equations and you take all the things that are happening into account, then you can start at least building the mathematical models. And one of the things that you enter is sort of the world of strange attractors and Lorentz attractors. So this is a picture of a Lorentz attractors that I put together that is now kind of driven by the singlet state and the interactions of the photons between the coil and the spins in the system. And these kind of systems have really interesting properties, such as predicting the sort of well-known butterfly effect, that just very, very small changes in initial condition can change the entire dynamics of the behavior in the future. And so I've taken the multi-mode RASER equations and started to try to see if I can visualize them in a similar way to these Lorentz attractors, for example. And so here I plot, for example, the population inversion, the phase between two spins, and then the amplitude of the RASER that we observe. And in the simple case, it's basically like a black hole. It starts having some interesting dynamics, starts swinging around, but then it all collapses into one single frequency. And this is what we see in the spectrum, or rather in the FID, when the signal becomes very regular and just continues to be regular for a long time. Things get a little bit more complicated if you have the two-mode equations, but even just with using two modes and the equations for two modes, we can actually predict observed behavior even from systems that contain maybe more than two modes. So the reason why the left and the right here, experiment and simulation, don't look exactly alike is because the experiment has a more complicated spin system than the one used in the simulation. Nonetheless, the behavior that we see experimentally can actually be sort of predicted by these simulations. So you see at a very short amount of time, at very high polarization levels, things are rather chaotic. You have all kinds of frequencies going on at the same time, as shown by the black simulation. And then as time progresses, as you have a next burst of your RASER, things start to be a little bit more regular in the sense that two lines are developing in the regime of in the frequency regime of the two spins that you have in the system. And then as the polarization decreases, if we go down here in the panels, only one of the lines remains because that's the only line that has enough polarization to be above the RASER threshold. Good, so I guess that sums up my talk for today. I think parahydrogen is a convenient source of spin order. Optically detected FIP enables nanoscale and portable NMR, hopefully in the future. And by designing and engineering new systems to make continuous streams of hyperpolarization, we can hopefully provide sort of continuous observation of metabolism. And then with these parahydrogen pumped RASERs, I think we're really opening sort of new opportunities for physics explorations, I will say. Thank you.